Somewhere in the last 24 hours, you ate something that grew out of dirt. That is not a strange sentence. It is just usually an invisible one. Almost every calorie a human being has ever eaten came from a patch of soil, warmed by the same sun, watered by the same rain for about 10,000 years. If you lined up all the farmland currently feeding the planet, it would cover an area roughly the size of Russia and Canada combined, close to 4.8 billion hectares of cropland, pasture, and meadow. That is one of the largest engineered systems humans have ever built, except almost none of us think of it as engineering at all. We think of a farm as the opposite of technology, a green field left alone to do what it has always done. But that field is running out of room. Cities are eating it, one subdivision, one highway, one warehouse at a time. But here's the part most people never hear about. Researchers estimate that somewhere between 1.6 and 3.3 million hectares of prime farmland disappear under urban expansion every single year, and the losses are not evenly spread. In parts of Asia and Africa, the cropland being paved over is often more productive than the global average, meaning the world is losing its best soil first, not its worst. In China specifically, one national land use study projected the countries could lose several thousand square kilometers of farmland a year through the 2020s, even as its urban population climbs toward 920 million people. Fewer fields, more mouths, and a shrinking margin for error. That is the quiet math behind almost every headline about food security. In 2023, a research team at the Institute of Urban Agriculture, part of the Chinese Academy of Agricultural Sciences, switched on something in Chengdu that approached this problem from a completely different angle. If you enjoy videos about Chinese engineering solving problems in ways nobody else has managed, hit like and subscribe so you never miss the next one. Why did it take this long to try growing food somewhere other than a field? The honest answer is that soil was never the problem, soil was actually the solution. For 10,000 years, soil did an enormous amount of work for free. It held water so crops did not need constant irrigation. It hosted microbes that fed nutrients to roots without anyone measuring a single gram. And most importantly, it captured sunlight across acres at zero energy cost, because the sun was already going to shine whether or not anyone farmed underneath it. Early attempts at growing food indoors in greenhouses and warehouses ran into a brutal trade-off. Replace the sun with electric light, and you replace something free with something expensive. Lighting, heating, and cooling a multi-story building 24 hours a day is not a small bill. It is often the single largest operating cost a facility has. For decades, that math simply did not work at any meaningful scale. You could grow lettuce in a converted shipping container as a novelty, but feeding a city that way would have bankrupted almost anyone who tried. Even the people who wanted this to succeed were fighting basic physics. More light means more yield, but more light also means a power bill that grows just as fast as the plants do. Japan and parts of Europe had actually experimented with early plant factories decades before China entered the picture seriously. But those early systems were built with a fraction of today's LED efficiency and none of the automated AI-driven control that makes fine-tuned light recipes practical at scale. So, agriculture stayed where it had always been, spread across flat land, dependent on weather and vulnerable, every time a city decided it needed the space instead. The pressure that changed everything was not stronger fertilizer or a genetically modified seed, it was light itself, and specifically, how precisely you can aim it. The Chengdu facility stands 8.8 meters tall and holds 20 stacked cultivation layers inside a footprint of roughly 200 square meters, smaller than a basketball court. Stacking layers is not new. Greenhouses have tried it before, but stacking layers without wasting energy on every one of them is the part nobody had solved. The researchers built what they call a plant light formula, a database of more than 1,300 specific lighting recipes covering 72 different crop types. Each recipe blends red, blue, yellow, near ultraviolet, and near infrared light in different ratios depending on the exact growth stage a plant is in. Think of it less like a light switch and more like a musical score, every wavelength timed and mixed for a specific moment in a plant's life. No more light than the plant can actually use, and no less. That precision is the difference between paying for light, the plant absorbs, and paying for light that just becomes heat in the room. Layered on top of the lighting system is a fully automated production chain, seeding, transplanting, nutrient dosing, and harvesting, run without a single person walking the floor day to day. Sensors track humidity, temperature, and nutrient levels continuously, and an AI control system adjusts conditions in real time rather than on a fixed schedule. Because the crops never wait on a season, a single layer of lettuce can be harvested roughly every 35 days, and the facility as a whole produces more than 10 harvests a year, regardless of what the weather is doing outside. Deputy officials at the Institute have described the system as the most densely layered plant factory in operation anywhere in the world, and staff have put a specific number on that density. Yield per unit of growing area can reach up to 120 times that of conventional open field farming, 120 times the food from a footprint smaller than a basketball court. That is not a marginal improvement. That is a different category of farming entirely. And the researchers were careful about something else. They bred their own crop varieties specifically for this environment, rather than forcing an ordinary outdoor seed to perform under artificial light, which is part of why the yields hold up harvest after harvest instead of degrading over time. Inside the building, 16 robots work a 10-meter-tall rack system, tending roughly 24,000 individual plants growing across that same 200-square-meter floor. Researcher Wang Sen, who helped develop the lighting system, has described the light itself as the real secret, adjusting the fill light at every growth stage until the team found what he calls an optimal recipe for each crop. And this is not confined to lettuce anymore. The same institute has already commercialized a second facility in Chengdu's Wenzhong district, an 11-layer vertical strawberry farm covering 2,300 square meters, producing an annual yield of 73 metric tons, 30 to 40 times what the same footprint would produce as an open field. That matters because strawberries are notoriously harder to grow indoors than leafy greens. They are more sensitive to light and humidity, and proving the model works on a second, trickier crop is a much stronger signal than one lucky result with lettuce. The steel and light challenger nobody saw coming came from a company most people outside agriculture have never heard of, a Xiamen-based firm called Sananbio. Sananbio began as a joint venture between one of the world's largest LED manufacturers and the Institute of Botany at the Chinese Academy of Sciences, which tells you where its actual expertise sits, not in farming first, but in light and plant biology first, with farming built on top. Its flagship system, an unmanned vertical farming platform called Uplift, automates seeding, germination, transplanting, and harvesting in one continuous line. And the company says a 5,000 square meter facility running the system can produce 6 to 8 tons of fresh leafy greens every single day. That is roughly 6 times the output of an older style 6-layer indoor farm occupying the exact same footprint, without adding a single square meter of land. By 2018, Sananbio had co-founded a 20,000 square meter vertical farm in Singapore with a local partner, one of the earliest large-scale deployments of the technology outside mainland China. The company has since grown more than 300 different plant varieties without natural sunlight, everything from leafy greens to crops used in traditional medicine, proving the approach was never limited to lettuce as a novelty crop. What makes this pairing powerful is that the two breakthroughs solve different halves of the same problem. The Chengdu facility proves you can push density and yield to extremes inside a public research institute, while Sananbio proves the same underlying science can be packaged, exported, and run as an actual business in cities that have never grown their own vegetables before. The world starts copying almost as soon as the receipts get published. Sananbio has already formed partnerships to expand vertical farming across the Asia-Pacific region, working with a company called New Horizon. In South Korea, it partnered with a firm called Farm 8 to build out the technology for a market with some of the least arable land per person of any developed economy. In Japan, representatives were invited to present directly to the Japan Plant Factory Association, a country that pioneered early plant factory research decades earlier and is now studying China's density gains closely. In Europe, the company signed agreements covering lighting technology for growers in Spain and Portugal, while separate reporting describes ongoing collaborations reaching into Eastern Europe and the United Arab Emirates, where farmland is scarce and desert heat makes traditional agriculture genuinely difficult. Even in the United States, a Sananbio subsidiary was established specifically to bring the technology to North American growers. The institute behind the Chengdu facility itself has fielded interest well beyond Asia. Wang Sen has said multiple companies in Saudi Arabia and the United Arab Emirates have approached the team in recent years, specifically to explore cooperation. Two countries where farmable land is scarce enough that food security is treated as a matter of national strategy, not convenience. Closer to home, the institute signed a partnership with a company in Hong Kong to build a new vertical farm there, set to begin operations in the second half of 2026, combining vegetable production with agricultural education tours for the public. One research and development executive in the industry summarized the shift simply. The constraint was never really land or sunlight. It was whether the economics of artificial light could ever be made to work. And for the first time, in a growing number of these deployments, they do. None of this spread happened because of marketing. It happened because operators in completely different climates ran the numbers themselves and reached the same conclusion. For a receipt that is harder to argue with than a press release, look at the output of the Chengdu facility itself. A single 100 square meter automated module there is documented as producing 50 metric tons of lettuce per year, harvested continuously indoors with zero exposure to pests, agricultural chemicals, or contaminated soil. Because the growing environment is fully enclosed and sterile, the produce coming out carries no pesticide residue and no heavy metal contamination, two of the most persistent quality problems in conventional vegetable farming. Staff at the facility have been explicit that operating costs remain real. Electricity for lighting and climate control accounts for roughly 70% of total running expenses, which is precisely why the lighting formula breakthrough mattered so much. It did not eliminate the cost of artificial light. It made that cost survivable for the first time. Separately, at China's broader plant factory sector, engineers reported cutting energy consumption per kilogram of vegetables from an initial 31 to 42 kilowatt hours down to roughly 8.25 kilowatt hours, against an international benchmark of around 10. That is not a lab claim sitting in a journal somewhere. It is a monitored, operating, commercially selling facility in a real city, producing a real number every year. How big could this actually get if the model keeps spreading? Vertical farming's global market is projected to grow at a compound rate of nearly 28% between 2024 and 2029, and one conservative industry estimate puts the total global market size at around $22 billion by 2035. If even a fraction of the world's leafy green production shifted to facilities running at 100 times the land efficiency of a conventional field, the land freed up would not need to come from clearing more forest or draining more wetland to keep pace with population growth. It could come from giving farmland back. Picture every rooftop, every disused warehouse, every patch of unfarmable desert or degraded soil near a major city, quietly turned into food production without needing a single new hectare of virgin farmland. It also means shorter supply chains. A facility built inside or next to the city it feeds can cut the distance between harvest and dinner plate from thousands of kilometers down to a few, which matters for freshness and for how much fuel gets burned just moving lettuce around a country. That is the scale version of the story. Not China grew some lettuce indoors, but a genuine shift in where the marginal unit of food on Earth gets produced from. None of this means the transition is simple, and it would be dishonest to pretend otherwise. The vertical farming industry outside China has already provided a very public warning about what happens when the economics are not solved first. 14 controlled environment agriculture companies filed for bankruptcy in 2025 alone, including firms that had raised close to $1 billion each. Bowery Farming, once valued at $2.3 billion and backed by more than $700 million in venture capital, shut down entirely in late 2024. Plenty Unlimited, which had raised close to $1.2 billion from investors including SoftBank, filed for bankruptcy protection in March 2025 before emerging in a dramatically scaled-down form. Aerofarms, an early pioneer in the space, went through bankruptcy proceedings in 2023 and later closed its remaining large facility as well, laying off well over 100 people in the process. The common thread in nearly every failure was the same one Chinese researchers spent years explicitly trying to solve: energy costs that scaled faster than revenue, and systems too complex and too expensive to run profitably at the prices consumers were willing to pay for lettuce. Even the most efficient facility described in this video is not immune to that math. Producing 1 kilogram of lettuce there currently costs somewhere between 10 and 15 yuan, roughly $1.50 to $2, noticeably higher than open field lettuce, and researchers there have been explicit that this remains the bottleneck they are still working to close. That number does not disappear just because the lighting formula improved. It only becomes survivable rather than free. There's also a real gap in access. The capital needed to build a 20-story automated plant factory, or even a modest 5,000 square meter commercial unit, is not evenly distributed across the world. Wealthier cities with expensive land and strong logistics networks are the first to make the economics work, while regions that may need food security solutions the most often lack the electrical infrastructure or investment capital to build them at all. Regulatory approval for large-scale indoor agriculture also varies enormously by country, and technology transfer between nations rarely moves as fast as a headline suggests it should. The honest framing is not that soil is obsolete, it is that a second option now exists alongside it, imperfect, energy-hungry, and still economically fragile in parts of the world, but real, monitored, and already feeding people at scale in at least one city. Go back to that plate you ate from 24 hours ago. For 10,000 years, the answer to where did this come from was always some version of the same story: land, sun, rain, season. What is changing in Chengdu and in a handful of cities now licensing similar systems is that food no longer has to wait for any of those four things to cooperate. The unglamorous, invisible infrastructure of dirt and weather that has quietly fed every human being in history is, for the first time, no longer the only infrastructure available. That is worth pausing on because it rarely announces itself as history. It just shows up as a slightly cheaper bag of lettuce in a supermarket that used to import it from 4 provinces away. If this is the kind of quiet engineering shift that actually reshapes daily life, hit subscribe so the next one finds you. Considering how basic the problem of growing food without soil sounds, and how long it sat unsolved, what other everyday systems do you think are one overlooked breakthrough away from being completely rebuilt?